Using the sextant, we will look through this pinhole onto this mirror and clear piece of glass and find a body in the sky. We'll go into that in detail. We will bring the body down to the horizon and take a mark, which means read the chronometer or your wristwatch or whatever timing you have. We will then read the height of that body above the horizon, your horizon, and work the problem. So let's get ready to go into the site form. So you're going to be taught in class that the site form, the filling out of the site form is all important. That's how you will get the line of position that shows where you are. You need the date, which is the month, day, and year, and the name of the body. You get the name of the body from the star finder. It will tell you what body you took. You need a position, such as a DR of, in this case, 45, 30, 15 west. And you need to know a rough eye height above the water. So this information you fill out. You read the sextant and fill out this information. This is the raw sextant reading, 1834.3. Now you have to read the index correction and the dip correction in order to come up with a apparent altitude of the body. So the way you get that is to measure the horizon with itself. If the horizon is in a straight line while your sextant reads 0, then everything's fine. But this is a rare case. Normally you're off a decimal or so, which is a small amount, but still needs to be corrected. So you align the horizon up with itself. If the horizon is here and you align it, then you're going to read than you should have. If it's here, you're going to read less. So by aligning it, you will get the amount. And the word, if it's off, meaning off the horizon, you have to put it on, which is to correct it. If it's on the horizon, you have to put it off to correct it. So you will learn that in the class, but this is a reminder. Now the next thing you need to know is the height of eye that we're going to call the dip. Now the dip means that you are above the horizon. You're looking down at it. So here's the horizon, and you're looking, this is your line of sight horizon where it should be, but you're actually looking down at it, so therefore there's a correction here, and always this is a too much of an angle, so you have to subtract. But the book will tell you that. So you go in for the height of eye, which we said was 31 feet. And you get that out of the Nautical Almanac. Under dip. Go down to 31 feet the dip, and you find that the correction is 0.4. So you write that 5.4 on the site form under dip. So now we have corrected for the sextant error, called index error, and the dip. We take and add and subtract as necessary to get the apparent altitude. So now we have the apparent altitude. So the next thing we have to do is correct for refraction when it comes to a star. Refraction simply means this: the light from the star is coming directly towards you, but when it hits the atmosphere, it bends towards the perpendicular. So therefore, it reads higher than it actually is. Now this is a known calculation, so you can get it too out of the Nautical Almanac under Stars and Planets, and down to our refraction that we need under apparent altitude. So the refraction is a little more than 18, so 2.9 is the correction. So then you add or subtract that to get your observed altitude. Your observed altitude then is the distance to that star from where you are, measured by the sextant. We now have the height observed, and we have figured that out to be 1827.0. Now the next thing we have to do is to find out where that body is in the sky, and you could say on Earth, but really in the sky. So the way we find that is by the time. If you remember, we stopped it to the second and wrote that down. That was 0800 with 12 minutes and 5 seconds. So the first thing we do then is to go into the Nautical Almanac for the correct year. I'm using a 1973 almanac simply because I have them, and it works the same in this almanac today. There might be a slight different reading in the stars, but it still can be used. So we go in the almanac and we find February the 25th on the daily pages. We go down to 8 o'clock and we write down the reading from the almanac for 8 o'clock. 275, that's degrees, 02.6 minutes. So we put that on our form, 275.02. That gives us for the hour of 800. But we have to take and increase it because the actual time was 12 minutes and 5 seconds after that. So in order to get that information, we go into increments and corrections. Now the increments and corrections, by the way, we went in for Aries, I'll explain what Aries is in the classroom. But we also go down for the time left over, 12 minutes and 5 seconds. And that gives us an increase of 3 degrees 01.7. So we write that down. And we could add them up at this point. But this is only to say where Aries is. The stars are measured further by what is known as SHA. So we go in for that day that we originally talked about, February the 25th, and look for antares under stars. Let me home in on that. You can see antares is 11303.3 and south 2622.5. Both of those go on the site form. Then we can add those up and we get 39107.6. But you know that there's only 360 degrees in a circle. So we could subtract that before the next step. But in this case, we're going to also subtract our west longitude of 3008.6. Now when we do that, we come up with 361, which is actually 1 degree. Actually, the Starfinder can explain this by saying, first of all, we put ourselves at the 45 degrees north and 30 degrees 15 west. So this is 30 degrees 15 degrees west. Now the second thing we did was look up the first point of Aries, and if you remember, it was 275 and roughly 3 degrees more, 278. So we put Aries at 278. So there's 270, Aries is 278. Now, they said antares had an additional amount called sidereal hour angle of 113 degrees. Well, that 113 degrees takes us down the bottom where Antares is. So now we have the information we need, including the 1 degree we figured by subtracting our longitude. Now this gives us what's known as the local hour angle, and that's what we need to go into the next book to do the easy, really, math with the 229. It's going to figure things out for us. We know how far the observed body was by the sextant. Now we got to compare it with a computer reading of distance. The difference will be where we are. Now we have quite a bit of information. We know the date, 2/25/73, the star Antares. We know we're at 45 north and 3015 west. This is approximate. This is a DR. We also knew that we stopped that star's movement at 8 o'clock Greenwich Mean Time with 12 minutes and 5 seconds. So we looked at the sextant reading, 1834.3. We corrected that sextant with its errors, normal errors, and we come up with 1827. Now we know that this is the distance, you could say co-distance, to the star. If we subtracted this from 90 degrees, which is the horizon from our overhead, then this 1827 minus from that would give us the zenith distance, meaning from our head to the body and antares. We have quite a few facts there. We know the Greenwich hour angle of Aries that all stars are measured from is 275 degrees rough, 3 more degrees. So we know the star is pretty well positioned, its geographical position. We know it's equivalent to latitude, which is declination, 22.5. Now these are things I've already taught, and this is a backup tape. So we add those things together and we get 39107.6. We know that we could subtract 360 degrees to get the distance from the Greenwich mean distance from Greenwich to the star Antares. So we're going to go farther. We know that our longitude is 30, but we take and use the 07 that we figured, calculated, as our position, because we don't really know where we are. We only guess we're around 30 degrees. We had 30 degrees DR 15 west. Well, this 3007 is close to that. So we subtract our longitude from the GHA of the body, and it gives us 361. It means the body's 1 degree from us, really. So if we look at our 2-minute star finder, we can see the same thing here. And there's Antares, just to the left of our due south, bearing a 181. So we have some information, and off of the Starfinder we can also measure 18 degrees above the horizon. These are things that we can put on the site form or use as a guide to the site form. So let's go farther and do some more calculating, which really means going into the HO 229 and coming up with the distance computed to that star. We can compare the two, and in comparison we can find out where we are. We now have enough information to go into the site reduction tables for marine navigation, latitudes 30 to 45, and we can figure out the problem using this table without a lot of math. So let's do that. We have a lot of information now on the site form. Now the site form tells us that we have what's known as a local hour angle, which means the distance from us to the star along the longitude line is 1 degree. We know its declination is 22.5. That's pretty well the same declination and latitude pretty well means the same thing. But this is a south declination, where our longitude is a north. So that means contrary. So we can go into the tables now with this information. 1 degree local hour angle, declination 26, and latitude 45. Now when we subtracted our 30 degree longitude from the GHA of the star, we combined them really. So now we know the declination, the latitude, and the combined Greenwich hour angle and our longitude. So let's go into the tables and take a look at them. Okay, here we can see contrary. That means we're north, the body's south of us, or south period, southern hemisphere. The local hour angle is 1 degree, and the declination is 26. So we can read off this figure, a group of figures, and put them into our site form. From the 22, 29, we've got the information of 1859.6 with a declination correction of a minus 9.9 and an azimuth of 179. So we have to use these figures to figure out the difference from 26 to 22.5 and to come up with a correction to the information that we took out of the book 1859.6. I'll show you how to do that using interpolation table so that we don't have to do any high math. So we took these figures out of the book, the 229. The height for declination of 26 was 1859.6. There was a D correction, which means declination correction, of a minus 559.9 and an azimuth of the body bearing of 179. So we have to use these figures and correct them. This is the height for 26, but we have to correct it for an additional 22.5 because that's the true deck. So we use an interpolation table to do that. We go in for the deck increments, which is 22.5. We have to go into the increment corrections and correct for that 22.5. So we find 22.5, and our table said we have to go to 59.9. So we go over to 50 column and we add additional 18.8. I had 18.9. I made a mistake, which is very small. Okay, then we have to go over to this correction here, which is a smaller correction, because we have to correct for 59.9. We already corrected for 50, so have to go for 9 now, which is this column. Then we find 0.9, which is this column. So the other correction is 3.7. So the total correction then on the site form is 18.9, said 8 in the book, and a 3.7. Now these were minus because this was a minus. So then we subtract these two figures from the computed height, and we get the computed height total of 1837.0. So that's where the things come from. Now we had an azimuth of 179, but if you noticed, it was to the left of our meridian longitude, so it has to be subtracted from 360. So the bearing to the body then is 181. And this is what is shown also on the star finder. You can see it's to the left, and it's 181 degrees from our south line, or 1 degree over from our south line, which is 180. You can see that it's roughly 18 high. So we actually got almost correct information from the star finder. Certainly enough to support and say, hey, what we did in the site form must be correct. So that's how you work the site form. Thank you. Now that we have the site form filled out, we still have a few jobs to do in order to plot. One thing we have to do is making a decision as to whether this 10.0 miles is towards or away from the bearing of the body. Now, a good way for this to work is to say Coast Guard Academy. Okay? It means computer greater away. So if we look at this, we can see that the computer is greater. So it's away. We also, while we filled out the site form for Antares, we also filled out two others, because we need 3 lines of a position to be sure. So here's Denham. The same idea. We fill these out. It sounds like a lot of work, but when you open the book for one page, you can write down the GHA for the others. When you go into the yellow page, you can write down for the others, and so on. So after you get used to filling out the site form, it's not hard to fill out 3 rather than 1. Of course, you have to get used to it at first. But here's Denham. The same idea. We come down and we have to make a decision towards or away again from the azimuth. So we look at this. Greater, observed, towards. That's observed, so it's greater, so it's towards. 3.4 miles towards the bearing of 066.6 from the AP. The same thing applies with another site form we filled out, Vega. Now in this case, here again, Coast Guard Academy, computer greater away, computer is greater, so it's away from the bearing of 096.8 from the assumed position. So now we go to a chart. Now this is a chart with the plot already worked out on it. So let's take a closer look. So the first thing I did on this was to make the chart, because this is a universal chart. Now the way this universal chart works is on this outer scale we have the latitudes. We want this central latitude to be 45. So then we look for 45 on the outer scale, which is here and here. So then we take a straight edge and make a meridian there. Now that meridian is the correct ratio for this latitude, 45 north. This distance and this distance is correct for this Mercator chart. Now, down below here, you might see a graph. Now, this graph is for the longitude, and it's marked 45 here. So the length of this line is the same as the length of this line. So we get our bearings from the circle, but we get our latitude from this line and the numbers, and we also get our distance from this line with numbers. Now, as far as longitude, we use this for our longitude. 0, 10, 20, 30, 40, 50, and this is broken up into 2 miles. So this allows us to plot. Now the first, if you notice, I have down here DAV. This stands for Vega, Antares, and Denham. So I take the APs, such as you see here, the APs, the deck AP was 45, the AP for longitude is 3011.5, so we mark this 45, this is 30, and this is 31. So then we can take off of this scale and lay down each one of the APs along the latitude AP by reading the Denham, for example, 11.5. So we measure off 11.5 on this scale, and we mark Denham down so that we can do that with each one. So we put the APs for each one of the sites down. So the next thing we want to do is to, let's start with Antares. Antares, if you remember, was 10.0 away from 181. 10.0 away from 181. So we take parallel rulers and find 181 on the compass rose, move it over to Antares. And remember, Antares was 10 away, so we measure 10 miles, and we go away from 181 10 miles. So that gives you this line. The next one would be, let's say, Denham. Denham was 3.4 towards 066.6. So we put our parallel rulers at 066.6. We measure off the mileage, 3.4. We go to Denham with it. Measure off 3.4 and put a 90-degree angle down, which gave us this line. So the other one was Vega. Vega was Coast Guard Academy away, 8.4 from 096.8. 8.4 we measure off. On this scale, and it was away from 096.8. Parallel rulers away from Vega and 90 degrees to that. Gave us this line. So that's how you plot. Now this becomes a pinpoint fix. So we can now measure off the latitude and longitude. The latitude is 4509 and the longitude of the fix is 30 down to this scale. That's 10. So 14. So 30, 14. We can write the fix down. That's how you construct the chart, and that's how you use the chart to plot the fix that we wrote down and did 3. Thank you.